Assalamualaikum and selamat sejahtera. My name is Muhammad Firdaus Muhammad Shukri. My matrix number CE250084. So my first part, which is introduction. Numerical method are mathematical technical. They convert complex calculation formula to simple operation that are repeated so that value can be easily calculation by human or computer when the theoretical solution is too difficult or impossible to solve. Instead of numerical integration, the trapezoid method calculation the area under a graph dividends it into struggle side. Trapezoid sharpen well. The Simpson 1 divided 3 method provide much high accuracy because it fits the curve of the paraboloid to even pair of even subintegral. So in the industry world, the main function of the numerical method is to act as programming based to embedded or to enable in industry words, the main function of the numerical method is to act as a programming base to enable microcontroller software such as MATLAB and factory computer system to process the soft calculation of the real physical data such as electrical power load, temperature and flow in real time to effective machine automation. So my next slide, which is engineering problem. So you can see in automatical manufacturing facility, a power quality analyzer is developed to monitoring the dynamic activity power load, which is in kilowatt of production line over a 12-hour operation shift. Due to the circle operation of half automated machine, the power profile to modeled by the following not like linear equation. So you can see the linear equation we give. So find the value of two difficult numerical method to solve the identify engineering problem with same conductor and level of the port active using n equal to 10 uniform sustainable give a step size of h equal 1.2 hour. So my last part, which is methodology. So the project need to follow the step process to solve and engineering using numerical method. So the first, which is identify the problem and turn it into mathematical function. The second, which is solve the problem using trapezoid rule and Simpson 1 divided 3. In manual calculation, manual step need to get the aspect value. So the 3, using mathematical tools simulation such as MATLAB to run coding for both simulation. The simulation acts as a proof to verify the manual answer, and the last, which is final compare the result to see which method is more accuracy.
For this example, the trapezoidal rule is used to estimate the total energy consumption over a 12-hour period. The intervals from 0 to 12 hours is divided into 10 equal subintervals, giving a step size of 1.2 hours. The power values at each time point are substituted into trapezoidal rule formula to calculate the approximate energy resulting in 624.0252 kilowatt. This value is then compared with the exact value obtained from the integration of the given function, which is 624.3432 kilowatt. The difference between the exact and the approximate values is 0.3180 kilowatt. showing that the trapezoidal rule provides a very accurate estimation with only small error.
Okay, for the trapezoidal rules MATLAB simulation, which is we're gonna need to set up our codes, which is first step is a limit. We must setting up the limit, which is a equals to 0, b equals to 12, and n equals to 12. Then we're gonna set up our step size, which is h equal to b minus a equals per n. Then we're gonna put a step function, put our equation in the codes. F equals to t 45 plus 12 power of sin pi power of t per 3 plus 2.5 power of t exponent negative 0.1 power of t. Then we're gonna put our x values function. So we're gonna get a trapezoidal rules code fully functioning. We're gonna get our output, which is energy that trapezoidal rules get is a 624.1224 watts.
Next is Simpson's 1/3 rule. For this example, Simpson's 1/3 rule is used to estimate the total energy consumption over a 12-hour period. The interval is divided into 10 equal subintervals with a step size of also 1.2 hours. The function values are grouped into odd and even terms and substituted into Simpson's 1/3 rule formula. The calculation gives an approximate energy value of 624.3424 kilowatt. This result is then compared with the exact value obtained from integration, which is 624.3432 kilowatt. The error is only 0.0008 kilowatt, which is much smaller than the error from the trapezoidal rule. Therefore, Simpson's 1/3 rule provides a highly accurate approximation and is more suitable for this problem.
Okay, for the Simpson's 1/3 rules MATLAB simulation, which is we need to set up our steps, which is firstly is limits. We need to input the limitation of this equation, which is a equals to 0, b equals to 12, n equals to 12. Then we need to set up the step size, which is h equals to b minus a per n. Then we're gonna put a function steps, which is we put our equation at the function f equals to 45 plus 12 since pi over 1 per 3 plus a 2.5 power of t exponent negative 0.1 power of t. Then we're gonna put a x values function, because this 1/3 Simpson's rules are different from the trapezoidal rules, so it have additional function terms, which is we're gonna put odd terms and even terms to get our result by using the Simpson 1/3 rules. Then after all steps and code are finished, we're gonna run it, and the output we get is energy the Simpson 1/3 rule use is 624.3428 watts. Okay, for the part discussion, the numerical result indicate the both method of successfully approximately and exact value of the integral. However, Simpson 1/3 rule produce a significant and more accurately result with an absolute error of only 0.0008 percentage, and the percentage of error is 0.0000128%. So in comparison, the trapezoidal rules are generate an absolute error is 0.3180 and percentage error of 0.0509%. The difference is because of Simpson over 3 rule use a quadratic interpolation approach, which is better representing the curvative of the functions. Therefore, Simpson 1/3 rules is more suitable for this problem and provide a higher accuracy than the trapezoidal rules.
In conclusion, this project successfully achieved its objective by evaluating the total electrical energy consumption of a non-linear power load profile using a numerical integration method with n is equal to 10 subintervals. When cross-referenced against the exact value 624.3424 kW, Simpson's 1/3 rule proved to be much more accurate, yielding a minimum of true error 0.00128% compared to trapezoidal rule, which recorded an error of 0.0509%. Finally, through MATLAB validation, it was successfully demonstrated that numerical methods are an important tool in industrial automation, enabling microcontrollers and computer systems to efficiently compute complex physical sensor data in real time.